Okay, this is going to be our 7th video in our Sources of Magnetic Field series. In this video we're going to be covering section 28.7. This is applications of Ampere's law. So this is basically just going to be 3 examples that I'm going to do. The textbook does 4 examples. I'll do the first 3, and if you guys want a 4th one, you can find it in the textbook. Okay. So we're going to start off, but before I start off with the actual examples, I just wanted to note that Ampere's law, although it's powerful, and we're going to see its sort of power here as we do these examples, it's much like Gauss's law in the fact that its applications are somewhat limited. We can only really use Ampere's law in situations where there's enough symmetry that we can do the integral easily enough to make it worth doing, right? So we're going to see in this situation we're dealing with well, the first situation we're dealing with a very long straight wire. In the second one we're dealing with a long straight cylinder that's going to have a current running through it, and in the third case we're dealing with a solenoid. All of these are going to have a lot of symmetry, so we can kind of really simplify down the integrals. You can imagine if these things were much messier, you wouldn't be able to apply Ampere's law, or at least you wouldn't be able to apply it in such a way that you could solve the resulting integral and it wouldn't really get you anywhere. Okay, but where it is applicable, it's super powerful. So let's take a look at some of those examples. This first example, this is 28.7 from the textbook. This is the magnetic field of a long straight current carrying conductor. Okay, and if we remember how we built Ampere's law, we built Ampere's law by looking at the result for a long straight current carrying conductor, and then we kind of built Ampere's law out of that result. So we really expect that we should be able to very quickly pull the result back out of Ampere's law, right? It should be able to go both ways. And we're going to find that that is in fact the case, right? So I'm going to start off by writing down Ampere's law here. And let's remember, we're looking for the magnetic field outside of a long straight current carrying conductor. Okay, so we have Ampere's law. Okay, mu naught, and this is going to be I enclosed. Okay, so let's just take a second again to remember what this is telling us. This is telling us that if we take the integral around some closed loop of B dot dl, it's going to be equal to mu naught times the current that we're enclosing in this closed loop. Okay, and so when we're dealing with a very long straight current carrying conductor, what are we kind of looking at? Well, we can imagine a really long thin kind of wire like this, right? And let's say, well, okay, so this thing is very long, so it continues off in both of these directions. Let's say we have some current like this. Okay, so we have current running down the wire, and we're interested in the magnetic field at some point, say P out here. Okay, but we know that the magnetic field lines are such that they're forming concentric circles around this current carrying conductor, and so we're going to set up to do our integral in the easiest way we can. We're going to choose a path for our integral that runs basically along one of these magnetic field lines. So I'm going to draw a sort of circle here. I'm not sure if I'm going to be able to do a very good job of it, but you can imagine kind of circle that goes around this this wire at some radius r here. This will be our r. Okay, and so this is our path, right? This is the positive direction of our path as given by the right-hand rule here, but it also happens to be one of the magnetic field lines that we would find, right? So this is kind of like B, and it's our path, okay? And so because of this, we're going to have a bunch of symmetry that we can kind of take advantage of. So first let me rewrite the integral here. So the integral that we're going to want to do is basically this, right, around this circular path that I've just drawn. But because we have we have B always pointing in the direction of DL, right? We're breaking up this path into tiny little DLs, and B always points in the direction of that path because this is actually a magnetic field line, right? We end up having B parallel to DL everywhere along our path, right? And what does this mean? Well, this means that B dot DL can simply be rewritten as BDL. Okay, that's one big simplification already, right? Another important thing to note here is that because we're on this magnetic field line, everywhere on that line, i.e., everywhere along our path, our B is uniform. It doesn't change, right? Because B is not changing with R here because our R is constant. So I mean, be careful when I write it this way. I just mean it to say that B is not changing with R, but that's really because R is not changing, right? Our R is constant. And maybe rather than writing it like this and it being somewhat confusing, I'll just not bother to mention it. I'll just say it in words that along our path B is uniform everywhere. Okay, it's not changing. And so what does this mean? Well, this means that this integral that we're trying to do here, this B dot dl, well, this can be simplified down to a simple integral that's just B dl, right? And we've already talked about what this integral is going to be as we go around a circle, right? This integral of dl adding up all these tiny little segments of length as we go around the full circle is just going to give us the circumference of that circle. So we're going to end up with B 2 pi r, right? And now moving over the right-hand side of our equation here, right? We had the left-hand side, which is this line integral that we did. The right-hand side is just mu times I enclosed. But what's I enclosed? Well, we're enclosing only the current that's in the wire that we're looking at, right? So I enclosed is just I, right? And now all we have to do, all we have to do is just isolate B, right? So if we isolate B, we're going to end up with mu naught I over 2 pi r, right? And that is the magnetic field outside of a very long, very straight current-carrying conductor, right? This is the result that we found before using Biot-Savart, but it's also the result that we use to sort of motivate our discussion of Ampere's law. So it's not a big surprise that we're able to pull that result back out, right? But at least it's a good confirmation that we can do that, so we know we're kind of on the right track, and we can kind of see how it works going in this direction, right? We found a situation where we wanted to apply Ampere's law. We saw that there was a bunch of symmetries that we could make use of to kind of clean up our integral. Our integral becomes very, very easy. We just have to do the integral around a loop of that loop, which is a circle. It just gives us this 2 pi r back, and we can very easily isolate B. Let's take a look at a second situation here. Okay, so the textbook has some really nice diagrams for this stuff, so I copied those over here, but maybe I made them a little large. We'll try to work with it here. Okay, so this is 28.8 from the textbook. This is the magnetic field of a long, straight, cylindrical conductor. Okay, so you might say, well, this is the same as the wire we just did, and that's true, except that now we're going to be interested in the magnetic field inside and outside of this long wire. And so now, instead of what we did before, where we kind of treat the wire as though it's infinitesimally sort of thin, right? In this case, we're going to be interested in what's going on inside the conductor and outside. So we're interested in the magnetic field for small r less than big R and for small r greater than big R. We're going to need to solve for sort of both situations here. Okay, and how am I going to do this with it being on screen? I guess I won't really be able to. So maybe I'll just talk about the diagram first, and then we'll sort of build up the solution from there. Okay, so we're kind of zoomed in on the conductor here. We have a current running in this direction, right? The capital R is the radius of our cylinder here, of our conductor, and the small r is the thing that's going to change. When we're inside, small r will be less than big R when we're inside the conductor, and when we're outside the conductor, small r will be larger than big R, okay? And so we kind of already know what the solution is going to be outside, right? When we're outside of this wire, we're just going to end up getting back the same result that we got for any long straight wire, which is the result we just got above here, right? So we're going to end up finding that this is true when we're outside of the wire, but we need the magnetic field inside the wire as well, and then we're going to kind of plot the thing and take a look at what it looks like. So let's kind of get started with that. So again, we're going to pick a circular path here. A circular path inside the wire kind of looks like this inner blue circle that we have drawn, and outside it's going to be this outer blue circle that we have here, and it's exactly like the idea that we had in the previous case, right? This circle is basically going to be sitting on top of a magnetic field line, so everywhere our B is going to be uniform because our radius is not changing along this path. It's always at the same radius, and everywhere on this path our B is going to be parallel to our DL, right? So we can make big simplifications, and the way I'm just going to skip over the doing of the integral, and what we're going to end up with is we're going to end up finding that for both r less than r and for r greater than r, we're just going to find that b times 2 pi r, or maybe this is too much of a simplification. Let me actually just write out the integral and then sort of quickly reason why we can do this, right? We saw in the previous problem, we know this is Ampere's law, right? But we saw in the previous problem, oh, that looks too much like an M. We saw in the previous problem that this for all of our the paths that we're choosing here, this is just going to reduce down to b 2 pi r, and r will be different depending on where we are, but that's fine, right? So because of the symmetries and because of the fact that dl and b are always pointing in the same direction, we can clean this thing up, and we're just going to end up with b 2 pi r is equal to mu naught I enclosed. Okay, and so we're going to be interested in finding what b is. So right away, let's just go ahead and isolate b. We're going to have b equal to mu naught I enclosed over 2 pi r. Okay, and so we have two kind of cases here. We have the case where r is greater than r, and when r is greater than r, well, our circle encloses all of the current, right? It encloses the whole cylinder. So our I enclosed just becomes I. So r greater than r means that I enclosed equals I, and this means that our B is just going to be what we expect, mu naught I over 2 pi r. This is the result that we found above, right? But what about when we're inside the wire, right? So when we're inside the wire here, we're not enclosing all of the current. We're only enclosing some small part of that current, right? How much current are we enclosing? Well, we need to kind of think back to our discussions of our current density, and we can see that I enclosed is going to end up being our current density, which we gave the symbol J, times the area which we're enclosing. The area which we're enclosing is just the area of the circle that we're drawing inside our conductor, this sort of grayed out circle here, right? So that's just going to be pi r squared. Okay, and then we have to remember what our definition for J was. So J, our current density, is defined as our current divided by the area over which that current flows. That happens to be pi big R squared, right? So this is the current divided by the area of the full conductor, okay? And this is the area of say, one of these outer circles, the full cross-sectional area of the conductor, right? So if we sub this J into the I enclosed here, we're going to end up with I over pi r squared, that's capital R, and then pi small r squared. Pi's cancel. This thing is going to end up giving us I r squared over r squared, like this, okay? And so now we have our expression for I enclosed, right? So we can sub this back into our expression up here, and we can get that for r less than r, we're going to have an I enclosed that I just wrote down, but I guess I'll write it again. I r squared over r squared, and this means that our b in this case is going to be equal to well, just substitute in this value into the expression that we have above here, right? So we're going to end up with a mu, and maybe I'll just write it like this. I'll write it 2 pi r, and then we're going to end up with I r squared over r. This r is going to cancel with one of these r's, and we can kind of clean this whole thing up. This is going to end up giving us a b, which is going to be equal to mu naught I r over 2 pi, and this r should be squared, sorry, big R squared, okay? And so that is the magnetic field inside our large, or our somewhat thick-looking conductor, right? Because we're looking at the inside of it now. We can kind of write this as a piecewise defined function, and I'm going to do that just so that our plot below looks a little prettier here, but we're going to basically see it, that we can write it like this. If we define it piecewise, we're going to have our b equal to mu naught I r over 2 pi r squared for r less than r, and then we're going to have mu naught I over 2 pi r for r greater than r, okay? So that would be sort of our final piecewise defined expression for our magnetic field everywhere. If we were to plot this, we would get the plot that we see here, okay? And so what are we kind of looking at here? Well, we can imagine that we have our really large conductor here like this, right? So that's our conductor. Our current is running down this conductor, and maybe I didn't draw it that well, but you can imagine that right at the edge of the conductor. So inside the conductor, we have this behavior of for r less than r, we have this behavior that this goes like r, like b goes like r. And then as we leave the conductor, b goes like 1 over r, right? So inside the conductor, we have this sort of linearly increasing magnetic field, and then when we leave the conductor, we have this sort of 1 over r behavior as this thing kind of dies off as we go off to infinity, right? And so this is sort of what the plot would look like of the full range of r values for our magnetic field. So we can see that inside the conductor, we have this function monotonically increasing. It's kind of just increasing everywhere inside the conductor, and outside it's decreasing. And from the plot, we can very easily see that we're going to have a maximum here right at the interface where we go from inside the conductor to outside of the conductor, right? And does this kind of make sense where small r equals capital R? Well, what happens here, if I sub small r equals capital R, we just end up with mu naught I big R over 2 pi r squared. These are going to kind of cancel, and so we're going to end up with a mu naught I over 2 pi r. And if we sub big R into the small r here, we're going to end up with the same expression, right? So that's exactly what we want. Both of these actually do meet up as they come up on this point where small r equals big R, and we get our b max, which is this value here, okay? So that is the example of a long straight cylindrical conductor, where we're kind of looking at it inside and outside of our conductor. I have one more example I want to do. The writing down of the example here is kind of longer than the solving of it. So let's take a quick look at it. It's important to understand what we're sort of doing here, so let's read through it sort of carefully. So we have a solenoid. Let's remember what a solenoid is. A solenoid is like a coil. Well, actually, they talk about it here. Okay, so a solenoid consists of a helical winding of wire on a cylinder, and this is usually circular in cross section. So you have like like a circular core, and you wind a wire around it lots and lots of times, sometimes thousands of times. And these things can often be in several layers, right? So you layer down the first layer, second layer, and so forth. You layer it up, and you have thousands of windings around this thing. And then the wire, you simply push a current I through the wire, and your magnetic field inside the solenoid is going to take on the form that we kind of see down here. Okay. Now they've kind of simplified this a lot. They only show us like what, 1, 2, 3, 4, 5, 6, 7 windings here, but you can imagine that there would be, thousands of these windings. And already we're starting to see this behavior where we're getting a sort of more uniform magnetic field on the inside, and on the outside there's almost no magnetic field, right? Like it's much more spaced out, so the magnetic field is much weaker out here. You can imagine that if you keep doing this, if you keep winding more and more of this stuff up, you're going to get a stronger and more uniform magnetic field as you make this thing larger, right? And if you have a solenoid where the length, the sort of length in the x direction here, is much longer than the sort of radius of your solenoid, you're going to end up with a magnetic field that's basically uniform and pointing along the axis of your solenoid inside the solenoid, or certainly close to the center of the solenoid, but pretty much inside the majority of a solenoid if it's very, very long, right, and it has a lot of windings. You're also going to find that the magnetic field inside is much stronger than the magnetic field outside. Most of the magnetic field kind of dies off as you're outside of the solenoid. And you can kind of see that by what they talk about here. They have a sentence here where they say, exact calculations show that for a long, closely wound solenoid, half of the electric field lines emerge and sort of leak out of the solenoid, while the other half stay inside. So if you have a ton of windings and this thing is really, really large, and a bunch of them are stacked, a bunch of these magnetic field lines are stacked up on the inside, and then along that whole length you only lose about half of them, and the other half are all tightly wound on the inside, it's going to be a much stronger magnetic field, and it's going to be very close to a uniform magnetic field on the inside. Okay, so when we're doing this problem, we kind of want to imagine a very long solenoid made up of many coils, where it's very long and relatively thin, right? So we have a solenoid that we have a very uniform magnetic field inside the solenoid. Okay, and so if we have this kind of a setup, like I said, we're going to have a very, very uniform magnetic field on the inside, and this is going to lead us to the symmetry that we can apply Ampere's law easily to find what the magnitude of that magnetic field is. Okay, so we're going to use, and this kind of gets to the sort of punchline of the question here, we're going to use Ampere's law to find the field at or near the center of one of these solenoids that has n turns per unit length, right? So we're imagining like an infinite solenoid here, and we're not going to talk about the number of turns in the whole solenoid, but we're going to talk about the number of turns per unit length. So for some unit length, let's say we have some length L, we have n turns in that length L, okay? And this thing is going to carry a current I, okay? So let's try to get the magnetic field inside this solenoid, okay? So this is the beginning of our solution here. Instead of trying to draw this by hand, I figured I'd copy it out of the textbook because this is kind of hard to draw by hand. So what are we looking at here? You can imagine that we had our solenoid, so I'm going to kind of draw some stuff over here that I'll probably erase, but you can imagine we have a solenoid, lots of wire turns like this, and then we come and we cut this thing in half like this, right? And then we look at it from the sort of top down, right? What we're going to see is that we've cut all these wires kind of like this, and the way it was going before, these wires would kind of hook up, and the current was coming sort of up and out of this one, and it would run across and then go down into this one, and then run across the bottom of this, and then up and out of this one, and then run back down into that one, and so forth. And so we have all these turns, and the current is running through all these turns, right? And we can imagine that this solenoid is much longer than it looks here, right? We're just looking at the central portion. There's a bunch of turns here that we're sort of not looking at, right? But we're interested in finding the magnetic field inside this solenoid, and we know that if this solenoid is super long, and very tightly wound, well, this magnetic field inside here is basically uniform everywhere in the cavity. Okay, and because of this, this is going to make our calculation much easier. So we're going to choose a path that includes the sort of central region here somewhat, and it's going to enclose some of the current. It's enclosing all of these wires here over a length L, so it's enclosing n wires because we're going over some length L here, right? And we're going to place our surface, not our surface, I should say, our path in such a way that it kind of encloses these wires. Part of it's going to run inside along our magnetic field lines. Some of it's going to run perpendicular to the magnetic field lines. Some of it's running outside. And let's now sort of talk about what's going on along each of these sections, because we need to do the integral, and maybe I'll write the integral here again. But we basically want to do the integral over our closed loop b dot dl, and we know this is going to be equal to mu naught I enclosed. Okay, but so usually we have to worry about doing the integral along all of these parts, but now we can eliminate some of these parts. So first of all, we can see that outside of the solenoid, as we talked about, the magnetic field is much weaker than it is inside the solenoid, right? And if this thing is like infinitely long, then the magnetic field outside is basically zero. Okay, so if there's no magnetic field outside, then for this section of the section that we can label CD. So for section CD, we have b equal to 0 over that section. So this integral is just going to go to 0, right? The b is just going to be 0, and so this means that we have no contribution from our section CD here. Okay. Now for sections DA and sections BC, so DA and BC, well, there would be some contribution over here, right? Like there's going to be some contribution from the magnetic field, except for the fact that, or maybe I shouldn't say there's going to be some contribution, but at least this section of our path runs along an area where there is magnetic field, but it runs in such a way that our DLs are going to be perpendicular to B everywhere, right? Because our B points in this direction and our little DL segments are going to point vertically here. So everywhere they're going to be perpendicular to B, and what does this mean? Well, this means that B dot DL for every little section that we integrate over on both of these vertical parts is going to go to 0. All right? Maybe I'll write it like this: goes to 0. Okay? And so neither of those will contribute at all either, right? So we end up only really needing to worry about one part of our closed loop integral here. We just need to worry about the section along AB, right? Now, do we need to worry about AB? Well, we do, right? Because there is magnetic field. It runs parallel to the direction of our DLs. So we're going to pick up the full contribution there, but at least it runs parallel, so that's an easy way to sort of clean up that integral, right? We're gonna end up having to do, and maybe I'll write it like this. So we're going to end up having to do this integral, right? Originally we had to do this integral. We could have broken up this integral into 4 parts, right? We could have broken up this integral that's going to go from A to B of B dot dl plus from B to C, B dot dl, plus from C to D, B dot dl, and finally from D back to A, B dot dl, right? But we just talked about how this C to D section went to 0. This is the part up here where there's no magnetic field. This part went to 0 because there is no magnetic field. And then we talked about how these two parts go to 0 because the magnetic field is perpendicular to our tiny DL elements. So really this whole thing simplifies down, and we just have to do the integral A to B of B dot dl, right? and this is what's going to end up being equal to our mu naught I enclosed. Okay, except that the symmetry of the problem means that first our b is not changing in here, right? So b is uniform everywhere along AB. So we don't have to worry about keeping it in the integral, and even better than that, our b and our dl are parallel everywhere, right? So b and dl don't have to be dotted anymore. It just becomes, maybe I'll just write it here. This integral just becomes a b dl, and our b can actually come outside of the integral, so this is just going to be integral, well, b times the integral a to b dl. So we're just integrating across this we're integrating all these tiny little chunks of dl from a to b. Well, that's just the length of the line from a to b. What is that length? That's just L, right? So the integral just basically falls away. This just becomes L, and all of this just becomes equal to BL. Okay? And so cleaning this up one more time, we have BL equal to mu naught I enclosed. The only question left to answer here is, what is I enclosed, right? Well, I enclosed is going to be the number of wires that we have enclosed in our loop times the current in each of those wires. Well, how many wires do we have enclosed? We know that we have n wires per L, right? And we have a length L. So what is our I enclosed? Well, I enclosed is going to be equal to n L. That's the number of wires. This is the number of wires per unit length. This is the length times the current in each of those wires, right? So we can just substitute this back in. Do I have space here? I have lots of space. Okay, so we have BL is equal to NLI. I'm just going to cancel out these L's. They're non-zero, so we can just divide it out. And oh, be careful. I actually miswrote that. So we don't have NLI. What we actually have is mu naught NLI. Right? I need to substitute this into here. So we're gonna cross out this L, and what do we end up getting? Well, we just find that B, for our very long solenoid, inside the solenoid, the magnitude of our magnetic field is going to be equal to mu naught N times I. Okay. Again, that's the magnitude inside the solenoid. The direction of the magnetic field we can always get by the right-hand rule by looking at any of these wires, right? You can imagine just putting your right hand sort of on top of one of these, like let's say you place your right hand on top of this, right? Your fingers are going to curl in the direction of the magnetic field, because your thumb is pointing in the direction of the current coming upward, right? So you know the magnetic field here, like if you were just looking at this one wire, the magnetic field would go like this, right? And so because it goes like that, you can see all of these kind of just add up to give you a bunch of magnetic field lines going in that direction. This leads to another right-hand rule that you can use for solenoids that you can kind of see on this diagram over here. So again, you can kind of line up your thumb with the direction of the current on any one of those coils, and you can see the direction in which the magnetic field is going to be pointing, right? It's going to be pointing like that, right? And again, you can just wrap your right hand around the entirety of the solenoid in the direction of the current, and your thumb is going to point in the direction of the magnetic field. So there's just like all kinds of right-hand rules that you can use to remember all of these, okay? So we have our expression here. This is our expression for our magnetic field inside the solenoid. If we take a look at this plot down below here, we can kind of see that they've kind of illustrated it for us here. The solenoid is kind of thick compared to its length, so we see that we don't have a super uniform magnetic field for very long inside here. The uniform portion is like right around here. But you can imagine that if you extended this way out and you extended this way out, you would extend the plot such that this flat region would be longer, and you'd end up with something that looks like this eventually, right? And I mean, there'd be a little bit of a bump to it, but really more like more like that kind of thing, right? So as we make this thing very, very long, and its length becomes long compared to its diameter, you're going to end up with a longer and longer flat region here, and this corresponds to the really uniform magnetic field that we're talking about calculating inside one of these solenoids. Okay. Okay. So that's going to wrap it up for this video and for this this chapter. Actually, the textbook goes on to talk about magnetic materials in section 28.8. We won't be talking about that here. It's a kind of nice read if you guys want to give it a look, but we won't be using that material for right now. So we're just going to skip over that and move on to the next chapter. Okay. So I will leave you guys here with that, and I'll see you guys in the next one.